We're going to have to understand what a derivative of a function means and then determine derivatives of functions using limits. This is what's going to change. Probably tomorrow. So tomorrow we will learn rules and shortcuts, and it will seem as though once you learn a particular rule, one rule, you'll go, man, I could have done everything we've been doing so far from the very beginning without using limits. And you could. But part of learning calculus is learning how to do things the hard way. And then you get rewarded with being able to do things the easy way. Okay? The problem is, though, the problems get more difficult because you can do them easier. All right, let's get started here. In the past, what we have done is we have found slopes of tangents at a particular point, at a specific point where a is some number and f of a is the y coordinate at that point. And we've had those two formulas that we've become familiar with. What's very important is soon, well, when you get to the unit exam, you might see a question like the one we just did. But you will not, at the end of the unit, do that question using limits. You will do it a different way. Okay. Remember, the value that you obtain in either of these, what you obtain can be thought of as the slope of the tangent at that particular point, or as the instantaneous rate of change of the function with respect to x at that point. Are you with me? Okay. So what is the derivative of a function? The derivative of a function is another function that you can use not to calculate the y coordinate of the graph, but to calculate the slope of the tangent at any point on the graph. The derivative is a function of x. It's something that you put x into, but instead of getting y out, you get the slope of the tangent out. And that general expression, that function that takes an input of x and outputs the slope of the tangent, is called the derivative of the function. So this is where I started. The derivative of a function is another function that can be used to determine the slope of the tangent to the original function at any particular point. We use this we can use this notation. It's not my favorite notation. If I talk about f of x being a function, and we want to find the derivative of the function, which means we want to find a different function that loading x in gives us the slope of the tangent to f of x, that different function is f prime of x. This is f prime of x is a way of saying the derivative of f of x. I don't like it because, particularly with some people who write small, and some of us are not the neatest writers, okay? You miss that prime, right? There's a better way to write it, and we'll get to that later. But that's pronounced f prime of x. And again, we'll get to other notations, one in particular that I prefer later. The use of Formula 2 is a cleaner approach. If I can go back, in fact, to these two formulas, I'll tell you right now that if you use Formula 1 to find a general expression, the derivative, it's not going to always work. Well, in principle it will always work, but the math becomes so deep, the hole you dig by using it is so deep that it's almost impossible to climb out of. I'm not saying when we use the second formula to find the derivative, it's always a piece of cake. It's not. There's work involved. But you're going to be more successful. And in fact, that's why everybody uses the second formula. So keep this in mind too. The general expression for the slope, the derivative, needs to be found in terms of x and not a. And when you take a look at Formula 2, we can change Formula 2 to be basically the same formula, but we're going to be talking about x and not a. If I take this formula and I change a to x, it's the same formula, isn't it? I mean, why on earth, if we want a general expression for a slope, why would we want to say the general expression for the slope at a? Why wouldn't we just say at x? So if you take this formula 2 and change a to x, this is what you get. It's something you can work with. If you take formula 1 and change x to a, there's nothing there. It's going to be the limit as x approaches x, which doesn't make any sense at all, of f of x minus f of x over x minus x. It's not useful. It doesn't go anywhere in a general sense. So what we are doing is simply taking formula 2, what I've called formula 2. We're, modifying it by changing the a to x, because we don't want to fool ourselves. It is about x, not a. And this is the definition of the derivative. The slope of the tangent on the top formula as h approaches 0 of f of a plus h minus f of a all over h is the slope at a specific point, x equals a. The formula on the bottom, the limit as h approaches 0 of f of x plus h minus f of x all over h, is the slope anywhere. Anywhere, so that's the derivative. That's the definition of the derivative. From now on, if you're asked in calculus to determine the derivative of the function from first principles, it means to do this. Even later, after I show you the shortcuts and the rules, starting tomorrow, I still expect you to be able to use this formula to find a derivative. So this is the derivative of a function, and I want you to note that it makes reference only to x. Like literally only to x, because h is going to become 0, so there will be no h's. Since h is approaching 0 at some point, h equals 0 will be substituted, and you're going to be left with an expression that contains the variable x and other numbers and operations. So example 1, what is the derivative of this function? How many of you, I'm just curious, because I've dropped some hints along the way, some breadcrumbs along the way. How many of you know what the derivative of this is going to be? Because we did some of this about a week ago. Teague, do you know what it is? It's going to be 2x plus 2. So Teague's picked up on one of many rules that we will learn starting tomorrow. It's going to be 2x plus 2. How many of you knew that? No. It's not obvious, and I'm just curious, Teague, if it was f of x equals 3x squared plus 8x, what would the derivative be?
6x plus 8.
It would be 6x plus 8. So there's, and some of you still haven't got it, and that's okay. You have to be taught it, but there's a rule. So how are we going to find the derivative of this? We're going to write that the derivative, f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And I can't tell you how difficult it's been for me every time I've written the h formula with a's not to put x's in, because that's what it becomes. So what does f of x plus h mean? F of x plus h means that we are going to have to substitute in x plus h everywhere there's an x in the function, right? We go from f of x to f of x plus h. The x is changed to x plus h, which means this is the limit as h is approaching 0 of x plus h quantity squared plus 2 times x plus h, and then minus f of x, which is x squared plus 2x, of course, remembering to put that in brackets. How many of you remember we have done these problems before, except we were using a, and it was just kind of a, at the time I said, it's not a big deal, but hey, let's try something. That was to get you ready for this. This is over h, and hopefully you will remember what I told you when we tried these using a. If you expand things out, there has to be a factor of h in every term in the numerator. I mean, I hope it's clear that when you put h equals 0 in, you're going to get 0 over 0. Even looking here, this is your eyeball, even looking there, if you put 0 in for h, the top becomes f of x minus f of x. The bottom is h. You're going to get 0 over 0 when you put h equals 0 in. This function we know as a parabola which is continuous over all real numbers, which means there is a slope of a tangent everywhere on the function, so the derivative must exist. I would go so far as to say that it's always possible to find the derivative of a function. Whether the derivative is defined everywhere is a different issue. Okay? If, and we'll talk more about this later, if a function is only defined, say, from x equals 1 to infinity, the derivative of the function will still exist, it just won't exist everywhere. It won't even exist at 1, but it will exist greater than 1. And there's a reason for that I'll get to later. I want to show this to you because I think I just lost some of you with saying that verbally. If I told you that we have a function, a little off topic here, but where this is 1, the function has a domain of x is greater than or equal to 1. Would you agree? The derivative is not defined at 1, but it is defined greater than 1. What is the reason for that? Well, the derivative is a limit. It's the limit of the slope of the secant as a point approaches the point of interest. But a limit has to exist on both sides. And we can talk about a slope of a secant here getting closer to the slope of the tangent from the right, but it doesn't get closer to the slope of the tangent from the left because there's no function on the left, so the limit doesn't exist on the left. So the derivative can't exist at that point. Believe it or not, there is no slope of a tangent at x equals 1 on this graph. It doesn't exist. You can't say there's a slope there. Anyway, we need to expand this out. And the algebra here with this question is not difficult. This becomes the limit as h is approaching 0 of x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x over h. And I just found myself on cruise control there without even thinking, so I'm going to double check everything. X plus h times x plus h will give me the x squared plus 2xh plus h squared. That's fine. Then we expand the 2 times the x plus h, and that looks okay, and I'm subtracting those two terms. So we get, of course, the x squared here and the negative x squared annihilating each other. We get the 2x and the negative 2x taking care of each other. And everything that is left is in terms of h. Or I shouldn't say that because sometimes I suppose you could, no, you can't get a number. Everything that's left is in terms of x or h on the top. So now we can simplify this one step further. I would give you the advice to resist the temptation to just go right into the answer from here. It's easy to make a mistake. This stuff that I've highlighted is in the way visually. So we have 2xh plus h squared plus 2h. Now listen, I'm not telling you you can't factor the h out at this point in time. I'm just rewriting it for the class. So now I can write this as a limit as h approaches 0, and the argument in the numerator has a factor of h. There's a factor of h in the denominator, and now we can put h equals 0 in, and when I do, I get 2x plus 2, which was what we knew it was to begin with, because at least one person has figured out a way to weasel maneuver their way around the limits. So we end up with 2 times x plus the 0 plus the 2, which means, don't forget, this is f prime of x. And you don't have to write f prime of x equals all the way down. You do have to write limit, limit, limit. But f prime of x is equal to 2x plus 2. And by the way, just so you know, and I have a feeling based on some expressions I saw earlier, I think there's 3 people in the room who have picked up on a shortcut. I mean, if I ask those 3 people, to find the derivative here, they may think they have an idea, but they have no idea, okay? They don't. There's no, you can't go from the rule they've discovered, which is a very basic rule we'll learn tomorrow, to something as simple as this. It's different. Okay. All right, any questions with our work there in finding the derivative? Incidentally, the derivative here would be negative 3 over x minus 2 squared. Don't try to break that code, because you're not going to be successful. All right, let's move on. Let's take a look at the next part of this question. What is f prime of 4? So f prime of x was 2x plus 2. F prime of 4 will be 2 times 4 plus 2. Listen, we're using function notation here the same way we would use function notation for anything. If I said, just going back here, you know, g of x, totally different question. G of x is this, and I said, what is g of 4? Well, it would be 4 plus 1 over 4 minus 2, right? The difference is when you put an x coordinate into an original function, you're getting a y coordinate. When you're putting the x coordinate into a derivative of a function, you're not getting a y coordinate, you're getting the slope of the tangent, which leads us to C. When we get here, f prime of 4 equals 10, what does that mean? Well, one interpretation is to say the slope of the tangent to f of x at x equals 4 is 10. You know, a different interpretation is really the same, because I think you should know what a slope of a tangent is. The second interpretation is to say at x equals 4, y is changing 10 times, I hate this word, but I've never been able to come up with a more meaningful description, faster than x. You know, if x is, it's an infinitesimal delta x. If delta x, though, is this big, delta y is 10 times greater. The issue in trying to wrap your head around that is delta x is that big. There's no delta x. It's 0. But this is loosely a good way of explaining it. Any questions with part B or C? All right. If f of x is the square root of 4 minus x, what is the derivative? Also state the domain and range of the, or the domain of the function and of the derivative. Those of you who have taken Math 30-1 have heard me say maybe a dozen times, maybe 24 times, there's never any nice tidy rule for talking about range. But domain is easier to approach, and it's more important. It's more important about what's going on in the world to talk about domain than range. If I'm applying calculus to a situation where x has to be, x is actually a temperature, but the conditions in the real world situation dictate that the temperature can't be below 0, then the domain leads me to solutions to the real world problem. It doesn't matter what the range is. The domain is what's important. And we'll do the domain of both the function and the derivative of the function in a second. So what will the derivative of the function be? Well, our only way to find the derivative so far is to use the definition of the derivative, is to use the derivative from what we call first principles. So it will be f of x plus h minus f of x all over h, and I've just rewritten the formula. Many of you might jump right into the first step after this without writing the formula. What does f of x plus h mean? It means we're going to take x plus h and put it in here. And before today, when we had the a deal going on, if a was 5, you'd be putting 5 plus h in. Here we're putting x plus h. So this becomes, the derivative of the function is the limit as h approaches 0 of the square root of 4 minus x plus h minus the square root of 4 minus x all over h. And I haven't been doing this for a while, so I thought I'd throw it in here. What's my mistake? Brackets, like that. You could walk into a lecture hall in university in a calculus class and go, and everybody would know what you meant, I hope. We need a set of brackets around the x plus h because we're subtracting it. Listen, how do you evaluate that limit? You could evaluate that limit a week ago. Other than the fact that there's an x here and not a number, you could evaluate that limit. You could say, well, how am I going to arrange it so that I don't get 0 over 0? Is it clear when you put h equals 0 in, the top becomes 0? Because you just have f of x minus f of x. And the bottom is clearly 0. The only tool, well, I shouldn't say the only, the one tool that stands out is to say that we're going to multiply the top and the bottom of this by the conjugate of that radical binomial expression, which is the square root of 4 minus x minus h plus the square root of 4 minus x. Whether you decide to, change that minus brackets x plus h to minus x minus h is up to you. Some people just leave the set of brackets in there. That's fine. We're not going to do anything with the bottom other than to rewrite it. So the bottom is h, and then the square root of 4 minus x minus h, plus the square root of 4 minus x. And I remember telling everybody a long time ago, well, a couple weeks ago, it's amazing how people will forget to write that conjugate on the bottom. And when I first said it, I could see everybody kind of go, well, I would never do that. And then some of you have done it in the meantime. It's very easy for some reason to just leave it out. We're going to multiply out the top. We're multiplying binomial conjugates. So I multiply the two radicals, root 4 minus x minus h, by root 4 minus x minus h. And I get 4 minus x minus h. And then when you multiply conjugate binomials, it's always minus. And we're going to multiply the radicals root 4 minus x by root 4 minus x and get 4 minus x in brackets. The algebra from here is not difficult. You just have to be careful with all your negatives. The limit as h approaches 0. Well, you should be able to do this. I'm going to do this in steps. This is what happens when I distribute that red negative into the 4 minus x. It becomes minus 4 and plus x. Clean that up a little bit. See, and you know what? I could really see myself doing this. I could really see myself putting, it's over h, and forgetting about that other thing. Don't do that. Looks okay. What do I have on the top? 4 minus 4, which is nothing. Negative x plus x, which is nothing. That entire top is negative h. I don't really have a problem here if you would have done this. Are we okay with that step? I don't have a problem, and I was going to do it, and I thought, geez, don't be lazy. I don't really have a problem with somebody doing that and then canceling the H's. It's kind of a non-standard practice, and I don't want to maybe give you bad habits that if you get to post-secondary, you're going to get slapped on the hand for mark-wise. Anyway, these cancel, and I'm left with a -1 on the top because negative h divided by h is -1. And now I can put h equals 0 in, and I get for this, which is the derivative of the function, I get -1 over root 4 minus x minus 0 plus root 4 minus, this h here should be an x. And a couple of minutes ago I asked, is everybody okay with that? Because I saw at least one person with that furrowed brow, and I'm assuming that that's what you were looking at. So this is x. Well, what do I get? I get -1, the derivative is -1 over 2 root 4 minus x. And this is going to play beautifully when we do the domain and range into what I already told you. The function, I want to write the function here, is root 4 minus x. So I want to spend some time talking Math 30 here, and this is for everybody. Even in Math 30 right now, you should understand everything I'm going to talk about. This function is the following. You're going to have to convince yourself that -1 times x minus 4 is the same as 4 minus x, which means that if we start off with the function root x, we are going to reflect it horizontally because of that -1, and then we are going to shift it 4 units to the right. So what this function looks like is that. And we can visually look at this and say that the domain, this is f of x, the domain of this is x is less than or equal to 4. Okay? You didn't have to determine the domain of it is x is less than or equal to 4 doing that. You could have said that this radicand must be greater than or equal to 0. So from an algebraic standpoint, we could have said that radicand, that's a 4, not a y, must be greater than or equal to 0. I move the x over, and I read it backwards, and I say x is less than or equal to 4. Are you with me? Okay. But remember what I told you for a function like this. Does the derivative of the function exist at 4? No, because the derivative has to do with a limit of the slope of a secant. And limits only exist when the left and right hand limits are equal. And there is no right hand limit. Which means, based on this picture, don't forget this is f of x, f prime of x should have a domain of this, right? It should. And there are moments in math that I really love because the math doesn't lie. It isn't that we made up some kind of arbitrary rule that, oh, well, the derivative doesn't exist here because the left and right hand limits are unequal. Look at the derivative function. Not only does 4 minus x have to be greater than 0, it can't be 0. Because if it is 0, you will be dividing by 0, and that's not allowed. So looking at the difference between these two, here 4 minus x can be greater than or equal to 0, which leads to this inequality with the less than or equal to symbol. Here, it just leads to this inequality, because otherwise you'd be dividing by 0. So there's a mathematical kind of demonstration that the derivative can't exist there. And I would say to you that that's my point in asking us to find the domain of both the function and the derivative. That just because a function has a particular domain doesn't mean the derivative exists everywhere in that domain. Oh, I'll go through the notation. That's Lagrange. It's a good ZZ Top song, Lagrange. But that's by a fellow by the name of Lagrange. He came up with that. It's still used. It's a very nice notation. This is the one I like best, dy dx. So that dy over dx means dy dx. It's not a fraction, okay? It's not a fraction, because dx is an infinitely small value of x. It's a really hard thing to wrap your head around. Sometimes instead of writing dy dx, we can write this. And you can think of this as being an operation called differentiation of y. So dy dx is the same as ddx of y. Or it's the same as ddx of f of x. And I'm saying it and writing it even though it's there because I think you need to hear it and how it fits together with the language. This is the best notation. It's what I tend to use 99% of the time. As many of you might know, Newton and Leibniz jointly developed calculus. This is 1600s, so it's not like 1700s? I'll have to look. It's not like they were on the phone with each other. They would write letters back and forth, and there's actually a book I have called The Calculus Wars that goes through all of the conflict between these two mathematicians. And Newton came up with his own notation, which is kind of laughable. Outside of the odd 80-year-old engineer, I don't know anybody that uses this to mean the derivative. Imagine missing that prime and then somebody goes y and they put a little dot over it. It's pretty risky. This is still used, but it's not used in high school. It means the derivative of y with respect to x. I will never use it. Okay? And that's Euler, Leonhard Euler. So on page 76, 10, 11, and 12, what you are doing here is you are using this formula. You're finding derivatives here. Now, Teague and a couple other people could probably find the derivatives of a, b, and c in question 10, no problem. But everything else would be guesswork. You do not need to do every one. I remember telling you yesterday or last week, we might spend 2 days on this. We're not going to. Then we're going to spend today on it. Tomorrow we're going to move on and start looking at rules. So, try some of these from 10, 11, and 12.